Mini lesson 1C, piecewise functions. Evaluate given the piecewise function. We have three pieces. We have 1/2 x if x is less than 6. We have a quadratic x squared minus 4x minus 9 if x is in between 6 and 10, with 10 not being included. And then we have the exponential 17 times 3 to the x minus 10 power for x is greater than 10. To find f of 0, we want to first determine which of the three pieces it's in. 0 is less than 6, so it would be in this first piece. And that gives you 0. F of 2 is still less than 6, so we're going to still use that first piece. 1. F of 6, well, 6 is going to be included in this one, in the middle one. So we're going to plug in 6 into the second piece. 3. For f of 8, 8 is in between 6 and 10, so we'll use that middle piece again. 23. All right, f of 10. F of 10 is not in either of those, so we'll say it's undefined. Because it's not in the middle piece, it's not in the last piece. And then for f of 12, 12 is greater than 10, so we can use 12 in the third piece. $153. So this is evaluating piecewise functions. The most important thing is to identify which piece it's in, and then after that, and only after that, can you evaluate it. Now let's look at a graph. Evaluate each given the graph. Then write a piecewise function from the graph. F of -6. -6 is right here, so it's 8. F of -2, it's a whole. It's not defined there, it's undefined. F of 0, that's 6. And then f of 3, that's also 6. To help us find the equations, we want to find the slopes of these linear pieces. The slope of piece 1, we could draw a slope triangle. Rise 1, run 2. And it's a negative slope, -1/2. The slope of piece 2 is a flat horizontal line. That slope is 0. The piecewise function. So if we extended this slope of piece 1, and it kept going, it would intersect the y-axis at 5. So our piece would be -1/2 x plus 5. And that is when x is less than -2. And for the horizontal line, y is always going to equal 6. So this piece is 6 when x is greater than -2. And then x is undefined at x is -2. Sometimes on piecewise functions, they will have a removable discontinuity where it actually is defined, but it's way outside of any of the pieces. Let's go to the next page. Sketch a piecewise graph that can fit this scenario. One spring day, Brianna noted the time of day and the temperature in degrees Fahrenheit. Her findings are as follows. At 6 a.m., the temperature was 50 degrees Fahrenheit. For the next 4 hours, the temperature rose 4 degrees per hour. For the next 2 hours, it rose 2 degrees per hour. The temperature then stayed steady until 6 p.m. For the next 2 hours, the temperature dropped 2 degrees per hour. The temperature then dropped steadily until the temperature was 61 degrees at midnight. On the set of axes below, graph Brianna's data. This scenario has several pieces to it. At 6 a.m., it was 50 degrees. So we'll find 6 a.m. and plot the point where it's 50 degrees. For the next 4 hours, it rose 4 degrees per hour. So 4 hours after 6 a.m. is right here. So it's 4 degrees per hour from 6 a.m. to 10 a.m. Each of these squares represents 1. So 1, 2, 3, 4, 1. 1, 2, 3, 4, 1. 1, 2, 3, 4, 1. And then 1, 2, 3, 4, 1. That was for the next 4 hours. For the next 2 hours, it rose 2 degrees per hour. So instead of 4, 1, it's going to be 2, 1. The temperature stayed steady until 6 p.m., so that means it doesn't rise or fall. So that's what happens right here. And then for the next 2 hours, the temperature dropped 2 per hour. So that was 2 hours. And then the temperature then dropped steadily until the temperature was 61 degrees at midnight. So 61 degrees at midnight. Be like right here. And so there would be the rest of the line. So it rises, it rises, it rises. It's constant, and then it falls. Write a story that fits the piecewise graph below. Let's write one together and then write a similar story as well. So let's have one story right here and one story right here. Let's do this as an example. Jane climbed 2 flights of stairs, then went to class. When she was finished, she then walked back downstairs to the basement, then went directly back up to the ground level. Now pause the video and write a similar story right here. Special piecewise graphs. An absolute value function is a special piecewise graph that connects 2 linear functions with opposite slopes. One has a positive slope and one has a negative slope. Let's look at this one. This one has a piecewise function of negative x minus 4 for x is less than negative 4, and x plus 4 for x is greater than or equal to negative 4. Now for these, you could put either of them as equal to. The absolute value equation for this one would be y equals the absolute value of x minus or plus 4, and you don't add or subtract anything to it. The formula for these is y equals a absolute value of x minus h plus k, where a is the slope of the right side and h and k is the vertex. Right, the x-intercept is at -4, 0, and the y-intercept is at 0, 4. The vertex is also at -4, 0 in this case, and then the axis of symmetry is the line that goes through the vertex at x equals -4. The range would be y is greater than or equal to 0, also known as 0 to infinity in interval notation. The translations from y equals absolute value of x would be left and neither up nor down, and there's no reflection. If it did have a reflection, the shape would be an upside down V instead. Let's look at this example. We have our 2 pieces. The slope of the right piece is going to be negative in this case. so -1. So our absolute value equation is y equals negative absolute value of x minus 3 minus 2. It does not contain an x-intercept, so we'll write none. The y-intercept is at 0, -5. The vertex is at 3, -2. The axis of symmetry, the light goes through the vertex, is at x equals 3. And the range is y is less than or equal to -2, also known as negative infinity to -2. The translations for the parent function y equals absolute value of x. It goes to the right, it goes down, and it has a reflection. Here are some other special piecewise functions. We have the floor step function. For that one, you always round down. So for example, 1.1 would be 1, 1.9 would also be 1. And that function would look like this. There is a closed point on the left side of each step, and there's an open hole on the right side of each step. And then for the ceiling step function, you always round up. So if you had 1.1, that would give you 2. 1.9, that also gives you 2. For this one, the right side is the side with the closed point, and the left side of each step is where it has an open hole.